Hello and welcome to the third in a series of programmes live from the British Science Festival in Aberdeen. My name is Chris Smith and I'm joined by Martha Henriques and also Andy Holding. Hello to both of you.
Thanks, Chris. Also coming up, we'll find out how the visual world maps itself onto the brain.
And we'll get the latest news from the Large Hadron Collider and find out why having an abandoned mine under your house could be good news for your heating bills. If you'd like to take part in our programme, then you can, of course, tweet at Naked Scientists. You can also comment on our Facebook page. That's at facebook.com/TheNakedScientists. Our email address, as ever, is chris@thenakedscientists.com. Now, Martha, what have you been looking at today? What have you got for us?
Well, one of my highlights of today was a talk by Fiona Henriques, not just because she shares my surname, no relation, about a common microorganism called acanthamoeba. Acanthamoeba lives in water. It's in the sea, lakes, tap water, and even bottled water. And it's usually harmless to humans, but it can start causing a real problem if it finds its way onto contact lenses. The hydrated, nutrient-rich environment between the lenses and the eye is ideal for them to grow, and a full-blown infection can lead to corneal scarring and blindness. Luckily, these infections are quite rare, with around 75 cases in the UK per year, and these tend to be in immunocompromised individuals, so people who have maybe had an organ transplant and are on drugs to suppress their immune system, and AIDS sufferers are also at risk. And these infections pose a real problem because these aren't bacteria, so we can't use antibiotics against them. And we have many cellular structures in common with acanthamoeba. So if we target any of those structures, we'll also be targeting them in the patient. But one potential avenue for research Henriques is looking at is using a herbicide agent to tackle infections, because acanthamoeba are fairly closely related to plants, so that might be one way of tackling infections without harming the patient as well.
I'm quite surprised you can use something that will kill grass. I mean, are you seriously going to put that in your eye?
Well, they've currently only done in vitro experiments, so there needs to be some clinical trials to make sure that this is safe for use in humans, but it's a potential treatment for the future.
I would hope so. I went to a device item. This was looking at ways to try and get people to stop smoking, actually. What this group is actually Steve Turner, who's a paediatrician here in Aberdeen. What he's been doing is putting into people's houses particulate monitors. And the idea is to tell them how dirty the air is in their house, because many people think that they're not exposing their children to very much smoke when they smoke, either by opening the back door and blowing the smoke out into the garden or just going out into the garden periodically. So what they've been doing is taking people who are smokers with children in the house. And this is important because if kids are exposed to tobacco smoke, they have an increased risk of getting asthma, and it can exacerbate asthma if they've already got it. So you want to reduce smoking exposure for those children, and also try and dissuade the parents from smoking. So they put these particulate devices into about 25 houses, and they also had a second group of about 25 houses that were controls. These are control houses where they just went in and gave people usual smoking cessation and risk mitigation advice. And they then got the parents to monitor their behaviour. And they actually found that when they went back a month later, the exposure in the houses that they had initially done the registered monitoring in and shown that there were high levels of particulates in certain parts of the house after the people had been smoking, it meant that they did change their behaviour. And one of the other big outcomes was they stopped smoking in the car as well. So it seemed to increase awareness that if you do this, you expose kids to particles in smoke that could harm their health. Unfortunately, the devices do cost a couple of £100, and so they're saying that actually in a cash-strapped situation, very difficult to get this implemented.
Well, it would be fantastic if they could roll that technology out on a wider scale. I also spoke to Essie Viding from the University College London about children at risk of developing psychopathy. These children show callous and unemotional behavioural traits, such as intentionally hurting other children purely out of interest. Viding and her team at UCL looked at what was going on in the brains of these children.
We've been interested in how these children's brains work when they process emotional stimuli. And we've compared them with neurotypical children, who are comparison children and who match these children on cognitive ability and socioeconomic status, but who are not antisocial, and also with other children with antisocial behaviour who are more emotionally reactive. And what we see when we show these children pictures of fearful faces in the scanner is that the typically developing children react to these pictures by activating a brain structure called amygdala, which is involved in processing salient information. Children who have callous and emotional traits show low amygdala reactivity, so they don't activate this brain structure as much as typically developing children do.
Understanding these changes in brain activity will help tailor behavioural interventions to minimise antisocial behaviour and prevent children developing adult psychopathy.
Martha, thanks very much. Well, it's been an exciting year for the Large Hadron Collider, the LHC, defending the speed of light, which we heard all about at the beginning of the year when scientists there thought that things were going faster than they should be, and also now the discovery of a Higgs-like particle. Well, today at the British Science Festival, a team of particle physicists, including Liverpool University's Tara Shears, have been bringing us up to date on the quest to understand the fundamental makeup of our universe. Tara, thank you for coming in.
Hi.
So what's the latest? Where are we with the search for this elusive particle? Have we found it?
Well, we've quite definitely found something completely new. We can be sure of that. And I know that the way that physicists are very reticent about claiming exactly what it is that's been discovered is something of a source of amusement for most people. What's clear is that we've seen something absolutely new in our data. And that something is doing the jobs that we think the Higgs is there to do. So really, I'm pretty sure that it's the Higgs. This is the particle we've been looking for the past 40 or 50 years since our subject started, and that's what makes it so amazingly exciting to us.
So can we all go home now then? So shut down
no.
CERN. Higgs has found, job done.
No, not at all. This is just the start of it, and I'm not saying that because I enjoy doing my job. I'm saying
Although you do have a vested interest.
But really, this is the tip of the iceberg. We've seen this discovery. We've seen something new. We're still not sure, though, exactly what it is. I have to stress that. It could be the Higgs that we've been expecting to see in our current understanding of physics, but it could be something more exotic. And that's really exciting. It could be something that gives us the first clue to some deeper mysteries in the universe that we're also trying to answer.
So what actually have you seen when scientists from CERN are saying we have seen evidence of a Higgs-like particle? What actually does that mean?
What it means is we've combed through trillions, millions and trillions of proton-proton collisions from the collider, looking for specific experimental signatures that are characteristic of what we'd expect a Higgs particle to have. These signatures are rare but clean, and that's the key. So if we see enough of them, then we can be sure we're not looking at some random combination that just is nature being cruel and teasing us that we're seeing a Higgs. We're actually seeing the real deal. And we have enough data now to really be confident that we're seeing something that isn't a random fluctuation. I mean, we're seeing something at the level of 1 in 10 million, that sort of chance of being a background fluke. So from that point of view, no, it's real. It's real, believe it.
People are saying this is definitely some kind of boson. Is it the Higgs boson? What do they mean when they make that fairly cautious statement?
So the sort of particle we're looking for a Higgs is the type of particle called a boson, and what that means is it has a quantum property. It has what we call integer spin. That's what makes a boson and not some other type of particle. But as to whether it's a Higgs boson, well, what we're looking at is to see if it behaves in the way that we expect the Higgs to behave. And what we mean by that is we're looking to see how it interacts with the other particles, how often it joins up with them, how often it decays to them. And what makes the Higgs special is that unlike the other bosons in nature that we know about that convey the forces of radioactivity or electromagnetism, this has, in a sense, a more fundamental role. It's responsible for giving the fundamental particles we know about mass, but that also has the knock-on effect of making the forces in the universe behave in the way they do. If you didn't have that Higgs there, then the universe would be completely different. You wouldn't have atoms, you wouldn't have stars, you wouldn't have us. Everything would zip round at the speed of light and wouldn't even coalesce at all. So it's at that level of fundamentalness that we have this interest in seeing this particular particle.
When people talk about you actually see the particle, and then on the other hand they're talking about a Higgs field, and the Higgs field is a bit like a gravity field. It's why things have mass. What's the difference between the particle and the actual field? How does one relate to the other?
In brief, because this field, this energy field that's the Higgs field, is invisible to us, the particle is the public face of the field. It's the only part that we can actually see. It accompanies it. What it means at a slightly deeper level is that if you think of space being filled with this sort of jelly-like, Higgs field-like substance, then a Higgs particle that we see corresponds to a ripple in this field, like a sound wave going through a room where the room is full of air. That's a good analogy to have in your head.
So these Higgs particles are everywhere, and they are creating the field or giving rise to the field around them, and matter interacts with that field, which is why matter has mass.
Pretty much. The Higgs particles are naturally associated, intimately associated with this field. You don't get one without the other. But fundamental particles moving through this field get their mass by that interaction with the field. So by discovering the Higgs particle, we know that the Higgs field is there. And because we know that the Higgs field is there, we know that that's how particles get their mass.
So how does the collision actually give rise to a Higgs particle? Is it that the collision in some way changes the field, and that means that we can see that signature sign of there being a Higgs particle there? Or are we creating a Higgs particle when we do those enormous collisions?
If you like, when we have a proton-proton collision at the LHC, we're really shaking the field and giving it sort of a big knock on the side and forcing a Higgs to come out. It's like, going back to my analogy of having a sound wave propagating through a room, it's like you've got an enormous drum at one end that you're beating to make these things happen. So our collisions make the Higgs visible for a very short instance of time. And then we see the debris that the Higgs leaves behind once it decays down.
And are they using protons just because they're conveniently A, heavy, and B, charged, so you can spin them at these enormously high energies to make these collisions? Theoretically, could you, if you could steer neutrons and give them equivalent momentum, could you do the same experiment with them?
If you could collide neutrons at the same energy, yes, that would work too, because what we're really looking at when we are creating the Higgs is colliding some ingredient of the proton, because it's a composite object, with some ingredient of the other proton. And the same would work with neutrons too. But what makes protons special is, just as you said, they're charged. That means that you can use electromagnetic fields to make them go faster. We need them to go really fast in order to create the energies in the collision needed to generate a Higgs particle sufficiently often for us to see it, which is why really protons offer us the only solution for being able to make it.
So what are the next steps now that you'll be focusing on at CERN? What are the big questions? Now you think you've got the Higgs, what's it going to take to firm this up? Where are you going next?
The very first question we have to answer is, what sort of Higgs are we looking at? That's very important. And to answer that, we need to look in much greater detail at the way it behaves and compare that behaviour to our theories to see if it's matching up with the Higgs we expect, or whether, as I said, it can be a more exotic version. But that's just one thing we're trying to answer with the LHC. We're also trying to understand what the nature of dark matter is, what it's made of. We're trying to understand what the nature of antimatter is and why we just don't have any in the universe anymore. These are all other areas of research that are ongoing. We're starting to get some unexpected and quite compelling hints of what might be out there. Nothing definitive yet, because it's early days for the LHC. So on our shopping list, besides working out exactly what the Higgs is working out what dark matter is, what antimatter is, how you can fit gravity into the whole picture, how many fundamental particles are. To be honest, the list goes on and on. There's so much to find out.
And since you mentioned it, just to finish off, do we think that antimatter interacts with a Higgs particle, or is there the antimatter equivalent of a Higgs particle?
That's an extremely interesting question. Antimatter has mass, therefore it must interact with the Higgs to get that mass. But as to whether the Higgs has its own antimatter counterpart, well, that depends very much on the type of Higgs that we're looking at. It could well, or it could be its own antimatter counterpart. I mean, really, it gets very science fiction-y at this point, seeing as we know so little about it. But yes, it's one of the questions we want to know about.
Tara, thank you. Tara Shears from the University of Liverpool. Martha.
Also at the festival today, a panel of researchers attempted to shed some light on how we perceive the world around us. We discovered why inattentional blindness prevents us from seeing obvious things simply because we're paying attention to something else, and discovered how the brain interprets objects at the edge of our vision. How our visual world is mapped in the brain, and what happens to the brain if we lose vision, is the focus of some research going on at York University, as Professor Tony Morland explained to Ben Valsler.
There's a map of the visual world in the brain, and it's a point-to-point mapping. So there's one part of the brain which represents the centre of our visual field, and as you move progressively across the brain, more and more distant points are represented, that being distance from the centre as you move out to the side of an image.
And is that all proportional? Do we need as much brain for our peripheral vision as we do for the central vision?
The central vision has a disproportionately large representation in our brains, and that's kind of makes sense in the context of the fact that our central vision is the vision that's most important to us. It's the vision that we use for reading and for looking at things, whereas our periphery is the part of vision that we use to orientate ourselves to things of interest.
When we're talking about vision in the brain, what is the brain actually doing in that region? Because presumably we need different bits of the brain to, say, look at a word, and then another part will tell us what that meaning is, and maybe another part will attach that to some memories. We're talking about the visual centre. What bit of that job does that do?
That is a really good question. The mapping that I've spoken about comes in multiple forms. So we're very interested in a number of these different maps. There's one which is very large. It's called the primary visual cortex. It's about the size of a credit card in each of your hemispheres. Beyond that, however, there are multiple maps. They become increasingly small, and the view is that they also become increasingly specialized. So when you talk about different roles, for instance, of extracting different information from our visual world, these additional maps may well perform those features. I have to say, we're really in the foothills of understanding that in the human brain. The last time I looked, there are probably over 20 different maps of the visual world in our brains, and we really don't understand which functions they perform.
How are we actually able to observe them? What are we doing now to shed light on these brain regions and how it maps out?
The very first map, I should say, was discovered a very long time ago by a neurologist in London who looked at gunshot wound victims, and he found out which part of the visual field people couldn't see in when they had a gunshot wound to a particular part of the brain. And from those studies of many gunshot wound victims, he established this map, this first map, the map we call the primary visual cortex. More recently, so at the end of the 20th century, we started using measures of brain activity, and in this case it's called functional magnetic resonance imaging. And we can show visual stimuli in different locations across the visual field and track the activity across the visual map in the human brain. So we go about assessing that map using that technique.
I assume, as with all things human, everybody is, to one extent or another, special and unique. Do you see different maps for different people, or is it such an important feature that it's conserved throughout all of us?
The first map appears to be conserved. I'd wager that early maps certainly are. We've been looking at the visual maps of normally sighted individuals for a long time now, and we don't see many discrepancies.
And that's for people with normal, healthy vision. What about people who've lost part of their vision?
Well, people who have lost part of their vision, and the people that we've looked at are people who've lost central vision. It's not so much whether they have maps or not, it's whether the primary visual map that we can measure most accurately and which is largest, whether that's changed in a way that might reflect reorganization of that map. We've seen a yes and a no answer to that question. There are individuals who are born with an anatomically perfectly normal retina, but the very center of it is not functional. Now, you would expect them to have laid down the sort of anatomical connections from their eye to brain, so you would expect their map to be pretty much normal on those terms. But as they develop, you might suppose that because they only have functioning peripheral vision and not central vision, that the map might change to accommodate that. It turns out that that seems to be a feature of their maps, that they do seem to stretch in that way. The interesting feature, however, is that that elasticity is not something we've been able to detect in patients who suffer from visual loss late in life. And this is a result of a disease called age-related macular degeneration. It's the most common form of blindness in the adult population in the Western world. And in those individuals, we don't see the plasticity or as elasticity, as you described it, of this map. So it seems to be very highly conserved once it's been laid down.
What does this brain reorganisation mean for perception of vision? So you've lost part of your vision, your brain then adapts. How does that compare to healthy people? Are there any ways we can actually find out?
There are phenomena that individuals experience when they lose central vision. They don't, for instance, walk around feeling that there's a big black splodge where they're looking. The idea might be that some brain mechanisms may be involved in sort of washing that splodge away, if you like. It seems clear that those mechanisms, certainly for the patients we look at, aren't really at the level of that very first visual map. So it may be further, what we would say, downstream in terms of the visual system that might occur.
So what's the next step for you? What else do you need to do in terms of this research in order to shed some more light on it?
The thing that we're really interested in at the moment is trying to understand that the parts of the brain that no longer receive information from the eye, what do they end up doing? They don't seem to have taken on a new role. They're starved of the normal input that they would normally receive. And there is some evidence that there is atrophy, so a reduction in that tissue. That is a bit of a concern because there are treatments now which are aimed at restoring the function to the retina. And once that's done, you've got to rely on the brain being ready to receive those signals. So we're just interested to see what's going on in that, what we might think of as a blank hole in the brain in terms of its responses. Is it really going to be healthy enough to take this restored function from the eye? And we're hopeful it will be, but that's another question for us to answer in the future.
Professor Tony Morland, who started that work while at Stanford University and now follows it up from his position in York. Andy, what have you been doing today?
As well as interesting science, there has been some interesting technology here today. I caught up with David Banks from Hollywell Consultancy Limited today to discuss a rather unusual bike.
Well, the bike is actually incidental. It's the heat pump that you should be looking at. The bike is just the means of driving it. A heat pump, put very simply, it's a device that transfers heat from, for example, a cold body to a hot body.
If I hop on this bike right now and start pedalling away, what actually happens?
Well, you pedalling the bike will drive a compressor, which in turn drives a cycle of refrigerant in a compression-expansion cycle. And without going into the details of how exactly that works, the net effect is to suck heat out of one side of the heat pump, the sort of intake, if you like, and reject that heat at a higher temperature through a heat exchanger, which effectively is the exhaust of the heat pump.
So how efficient is this? Because how much energy do we have to put in to pump it? Is it presumably it's less than the amount of heat we're transferring?
Yeah, otherwise there would be no point in doing it, of course. So a typical efficiency would be maybe 350% or 400%. If it's 400%, that means that if we put 1 kilowatt of electrical energy in to power the compressor, we transfer 3 kilowatts of heat out of the ground and get a grand total of 4 kilowatts of heat delivered to our home.
So are there any things we have to worry about if we start doing this? If we start pulling huge amounts of heat out of something, can something go wrong, or is this a nice free way of getting energy for our houses?
Well, it's both, yes. If it's designed properly, it can be a nice, not entirely free way of getting energy from the ground, because, of course, you still have to pay for a small amount of electricity. But there are things that can go wrong with it. These systems are complicated. You actually need to integrate a lot of skills, geological skills, architectural skills, plumbing, mechanical engineering. So it is quite complex to get it right. The other thing that can go wrong is simply, if you try and suck too much heat out of the ground, it'll get too cold down there, and eventually you can freeze the ground, and that can have all sorts of undesirable consequences like frost heave, formation of ice wedges in the ground, and this kind of thing. But if it's designed correctly by a well-informed designer and installer, it can be a very efficient way of providing heating to your home, both efficient in terms of cost and efficient in terms of carbon dioxide.
So if I hopped onto this bike right now, would I be able to get myself a nice chilled beer?
Yeah, if you would need it, because you would have to pedal quite hard. This is not an efficient heat pump, but it does work. If you pedalled hard enough and long enough, you would cool down the tank of water on the evaporator side of the heat pump to a temperature where you could chill a beer. The heat that you would have sucked out of that tank of water in the beer would appear at the condenser side of the heat pump as energy you could use to heat your house.
Can I cook a burger?
You'd be struggling to cook a burger, I think. But certainly to chill a can of beer, you might be onto a better bet with that.
David Banks was talking with Andy Holding. Thank you, Andrew. So how can we actually put the principle of heat pumps into practice in towns and cities? It turns out that scientists may have discovered a use for old mines. Dermot Campbell is an Edinburgh-based geologist with the British Geological Survey. So what's your idea? What are you proposing?
Well, the idea is that we use heat pump technology to exploit the resource which lies under a city, and we've been using Glasgow as a test case. Been using Glasgow mainly because we've been doing a lot of work there in the last few years, developing high-resolution 3D models of the subsurface of Glasgow. We've been working very closely with Glasgow City Council to help them in various regeneration and redevelopment projects. But one of the additional dividends that's come out of this very detailed modelling is that we've acquired a very good understanding of the extent of the abandoned mine workings which underlie very large parts of the city of Glasgow and the wider Glasgow conurbation.
How much of Glasgow is sitting on a mine shaft?
Well, looking at the Glasgow conurbation as a whole, it's approximately 50%. In fact, most of the eastern conurbation of Glasgow is sitting on top of mine workings.
How deep?
They vary up to a maximum depth of about 610 metres, but on average they're generally in the range of 250 to 300 metres deep as a maximum. But some of the mine workings are very shallow. Some of the oldest mine workings come to surface.
Are they still intact, or have they all collapsed?
Various mining techniques were used, and there have been various collapses of some of the very near-surface workings, which are the oldest workings. But by and large, as the mines developed, they started to use a technique called longwall mining, which actually allowed the workings to collapse as immediately after the coal had been extracted. So most of the collapse and subsidence took place a long time ago when the mines were actually active and working.
So what we've got underground will be layers of rock which is intact and therefore very strong and impervious, and it will be punctuated by these sort of lateral shafts where even if collapses happen, there's lots of debris, things can flow through there.
Yes, and the idea of flowing is the key principle in all of this, because once the mines had stopped operating, pumps were turned off because that's the only reason they were able to mine to the sort of depths that they did. They were pumping water out of the system to keep it dry. After the mines had stopped being active, the natural groundwater system was allowed to reinvade the rocks, reinvade the mine workings, and work its way back up towards near surface where it is now. So essentially the abandoned mine workings are now flooded. And the important thing is that it's an important aquifer, contains a lot of water, and that water flows very readily through the mine workings and through the tunnels which interconnect the mine workings to the shafts. That's the important factor that we can exploit, potentially, in using ground source heat pump technology.
So you could put a tube or a borehole down to some of these lateral shafts that are full of water at ambient temperature. Will this therefore exploit the fact that some bits of the mine are going to be at a different temperature than others, and you're using that temperature gradient?
Very much so. Now, the idea isn't entirely new. There are working systems, usually on a small scale, and in fact there's an example in Glasgow which has been operating now for 13 years, providing space heating for some 16, 17 houses in a housing association project. It was a very innovative piece of thinking by the architect who developed the project. And the deeper, essentially, you drill into the workings, the warmer the water is likely to get. We're not dealing with geothermal energy here, we're dealing with thermogeological energy, essentially energy that's coming from the sun. It's warming the surface and working its way down. But there is an increase of temperature with depth. And generally the idea is that the deeper you can drill into the system, the warmer the water will be. Therefore, there's that added advantage. You can then pump that water to surface, extract some of the heat using heat exchangers, essentially the technology we have in our fridges, and then return slightly cooler water to a shallower level in the mine workings. Now,
isn't that quite inefficient, having to move large amounts of water, because that's heavy? Could you not pump the refrigerant down, or the chemical used in the heat pump system? Would that not be easier?
That essentially would be the technology of what's called a closed-loop system. Now, they tend to work efficiently only on a very small scale, so if we really want to upscale the whole process, we need to think in terms of moving the water around the system in an open-loop way.
So you pull out some of the warmer water and extract the heat from it using the heat pump technology.
Yes.
And then return the colder water to a different part of the mine.
Yes, and a shallower part of the mine typically, and this is what has been done in the largest current working example of such a system in the southern Netherlands. It's a demonstrator project which came on stream in 2008. It had some support from the European Union Interreg Fund to get the project up and running, but developers buy the heat technology from a company that was set up by the local authority there.
Is there any risk, though, with doing this? Because you're putting water, albeit only a tiny amount cooler, in one part of the mine, having taken the energy out. This could potentially affect the pressure, could it not? Or the effect on the rock, it could make the rock contract or expand differentially across the mine workings. Is that not a risk?
I don't think pressure's the real issue at stake, because the sorts of volumes of water that we're moving around the systems would be tens of litres a second potentially. So we're not moving colossal amounts of water around the system. But certainly the change in temperature of the rock mass is something that we have to take account of, especially in relation to some of the oldest workings, which left pillars of rock in place holding the roof of the workings up. And colleagues of ours in Edinburgh University are looking at this aspect now and looking at the potential stresses that this might create. But we think on the sort of scale that we're likely to operate the process, it wouldn't be a major issue. But we've got further work to do on this aspect. It's certainly something that needs to be considered. But we also have other experience to draw on from the working schemes which exist already in the Netherlands, and other schemes are coming on stream in Poland, Germany, Spain and elsewhere.
That's very reassuring. But based on the maps you've made, how much energy do you think is down there in terms of the capacity of that system to supply how much of Glasgow, for example?
Well, we've used various ways of looking at this, but a flow rate method which considers the sort of borehole yields that you might get from mine workings and the temperature of the waters that you would be exploiting. We've come up with various scenarios, one of which suggests that using 4 boreholes per square kilometre in areas where there are mine workings, extracting up to 10 degrees centigrade, which is more than we would normally anticipate doing, you could potentially provide up to 40% of Glasgow's space heating requirements. And that's on a fairly sustainable basis for potentially up to 100 years.
How many people in Glasgow?
1.2 million people live in the Glasgow conurbation, 600,000 within the city of Glasgow itself, but about half of those live above mine working. So,
and would this be a sort of CHP-like thing where you'd have energy heat coming to one central facility and you would then distribute that around the houses?
I think this is highly likely, but this is where you need to start talking to power providers and other people who are really experts in this. But yes, we envisage this as being part of a mix of energy requirements. To make use of ground source heat energy, we really need to consider adaptations of the properties that you'd be providing space heatings for. They have to be well insulated, and new builds are possibly the best way of achieving this. And of course, Glasgow is embarking on huge building programs, so there may be real opportunities to do this.
Presumably Glasgow is not unique in having mine workings under it either.
It certainly isn't. No, in fact, a large proportion of the Midland Valley of Scotland, for example, lives above or close to mine workings, and there are major coalfield areas in northeast of England, the northwest of England, the Yorkshire coalfield, the Midlands, South Wales, and so on. So quite a significant part of the British population.
So if you get this working here,
workings,
then you could extrapolate this across the country.
Very much so, and that would be something that we would really like to see if it could be achieved. Yes.
Let's hope so. Dermot Campbell, thank you very much. That concludes our presentation today from the British Science Association Science Festival here at the University of Aberdeen. If you have any questions or feedback for us, then do get in touch. It's chris@thenakedscientist.com. You can go to our Facebook page, which is facebook.com/thenakedscientists, or you can tweet @nakedscientists. From us here in Aberdeen, thank you very much to Ben for producing, Martha helping me present, and Andy Holding. Until tomorrow, goodbye.